Yeah, you're good.
Okay, perfect. Thanks, guys. So I'm Nakul Gopalan. I'm a postdoc with Matthew Gombele, and I'm here to present my work on learning transferable symbols and language grounding from perceptual data for instruction following, which is clearly a mouthful, but we'll walk through each of those things one at a time. I'm a postdoc at Georgia Tech with Matthew Gombele, as Jesse already mentioned. So, now our perception of an intelligent agent that comes from movies looks more like this, where there's a general purpose agent that can do multiple tasks in the world. So there is Betamax from Big Hero 6 that can learn to do medical procedures, for example. And there's also a robot from Bicentennial Man that can actually learn to play music and read texts and interact with children and things like that. So we want a general purpose agent that can do multiple tasks and can learn to do multiple tasks when interacting with people. What we actually have are special purpose tools like packaging robots, car manufacturing robots, or toasters, which basically have actuators that perform programmatic behaviors. But what we really want is a general purpose tool that can learn to do all these tasks at the same time. So what we really want is the ability to program robots to do novel tasks. And this can allow us to do personalization. This can allow us to teach a robot tasks that we want it to solve. And you can solve tasks that might not come pre-programmed from an industrial robot, like, you want your robot to make candles, you want your robot to watch after your dog while you're away, and things like that. So you want a general purpose robot that you can retrain to do novel tasks, perhaps with use of language and demonstrations in some ways. So an example scenario might be this. So Rosie from the Jetsons is a big example because she can do a lot of home tasks in the Jetsons. And we can ask Rosie to clean the Kachina doll. And our house might be just filled with different objects that the robot might have no idea about. And so this is the Kachina doll, and it doesn't just come in that form. There are multiple types of Kachina dolls. And they, like, two different dolls don't look anything alike because they're handmade by Native Americans, and they're very special and expensive dolls. So cleaning them is actually an expensive, risky chore. So as soon as you give this language command to clean the Kachina doll to Rosie, she comes up with two problems. The first one is, what is a Kachina doll? And the second one is, how does one clean said doll? And what we know is that people can learn these novel behaviors from language in a few demonstrations, but then can we have robots do the same? So let's first look at the problem of what is a Kachina doll. And this problem is actually part of an older problem called symbol grounding that was described by Harnard in 1990. And when you say something like, go to the green room in the world, you have this problem where the green room is some symbol that you have uttered in the world, and it's referring to an object in the world, which is a referent. And the problem of symbol grounding matches a symbol to a referent in the world. We have covered this problem extensively for robots in a review paper that we wrote in 2020, specifically talking about the hardness of the problem of mapping language to some objects in the world, or any referent in the world, be it in a map or an object. The second problem that Rosie comes up with is, how does one clean a Kachina doll? And this problem I choose to solve with planning, with some symbols that we'll learn from high-level demonstrations. And what we really want to do is to give a demonstration of the robot going to the green room, let's say, and then learn some high-level symbolic information about going to the green room so that we can solve this in novel scenarios in different houses and things like that. So we want to plan given symbols, and we want to map language to these symbols. Cool. So given that, our objectives are to learn symbolic concepts that are useful for navigation and planning from unstructured demonstrations, and to map language to these symbolic concepts using some paired instructions. And then we want to plan over the sequence of symbolic concepts that we get in the world using an external planner. And this external planner can then be used in novel scenarios. The issues that you come up when you do this is that there is an unknown number of underlying symbols. We do not know in advance how many symbols there exist in the world. There are no labels for these symbols themselves. It's not like we know that we are going to need a green room and a blue room in advance. Given data, we just don't know how many symbols there are going to be. And then there is the high dimensionality of the data itself, where the data is high dimensional and you want to learn these crisp symbols from this high dimensional data. And I bet George would have talked about that earlier in the day. And what we have access to is only a small number of human-robot interactions, where the human can only annotate, let's say, tens to hundreds of trajectories, but not thousands of trajectories on the robot itself. And I think that that's important because a robot's arm might not survive thousands of demonstrations in the first place. Now, this problem of symbol learning has been attempted by people in the reinforcement learning community and the robotics community for a while. So there are a bunch of RL domains where people have tried to learn predicates and then solve reinforcement learning problems using the learn predicates. And then there's a bunch of robotics work where people have tried to learn symbols and predicates from demonstration data. But none of them actually involve any work with language or symbol grounding. Then there are classical NLP approaches that map natural language to some pre-specified predicates, and then they learn to map language to some weakly combined pre-specified predicates. But they're not trying to learn predicates from continuous data. There's a lot of modern work where people are trying to try to map natural language directly to trajectory simulated environment. I myself have one, that's the Stengel-Eskin 2021 work. But again, the problem with this is that all of this requires millions of demonstrations and tens of thousands of instruction pairs mapped with trajectories. And that might not be to actually collect on a real robot. So now I'll walk through a simplistic example of our approach. We ask our robot to go straight and take a right turn. And we can use something that segments trajectories into individual segments based on the type of actions that the robot is taking in the world. And once you do that, once you have access to this action data, you can actually see that when the robot is driving straight, the data looks significantly different from when the robot is turning right. Once you have these segments, you can actually learn termination conditions of these segments. So you have termination states that the robot gets to at the end of the segment, and you can then learn a termination state classifier based on the segments that you find in the world. So in this case, the robot might find two types of segments, one that maps to the end of the corridor and the other that maps to an open corridor after it's taken the right turn. And then you translate using any NLP pipeline to go from natural language to these termination states that you've learned from your data. So this is what our data collection pipeline looked like. We basically drove the robot around in the world, and we collected about 75 trajectories. And what we collected was lidar data, and then we showed the visual data to people on Amazon Mechanical Turk, and they gave us language data that mapped to the trajectories that the agent took. And then what we can do is we can take these actions and feed it to a change point detection algorithm that will give us these skills based on the actions that the agent took in the world. And for this, we use a specific framework called hierarchical Dirichlet process hidden Markov model, which only needs, which is a stick breaking process-based model. So we're only giving the model access to the actions that the agent takes in the world, which are y1, y2, y3 to yt. And there is some noise parameter between the actions that the agent actually took, z1. There's some noise when the agent actually performs that action in the world. So we provided the noise parameter going from these z's to y's. And we provide a parameter that actually allows the agent to create new skills. So beta is controlling the rate at which a stick breaks. That is the rate at which a new policy is considered to represent your data. And pi represents the policy, the action that's being taken in the world, given that you're in policy K. So all we show are the labels of the actions that the agent took in the world, a noise matrix, and the stick breaking parameter gamma, and we can basically learn the parameters beta and the policy pi given data. What's really cool about this is that it's unsupervised. It allows an unknown number of latent skills, and all it needs access to is the noise parameters to work well. This is a Bayesian method, old school, from 2011, basically. Once you actually feed this to your change point detection algorithm, you get segments like this, that the robot was driven straight for that many time steps, and the robot was taking right between these time steps, and the robot was then driven straight. What we can then do is provide the termination states that we got into a clustering algorithm. And then we can try to learn symbols over the clustered states. So we use a classical clustering algorithm called dbScan. And again, it's unsupervised. We don't need to specify the number of clusters that we'll get in the end. And the clustering algorithm just creates clusters for us. After that, we feed these clusters into a one-class classifier, a one-class SVM, which learns the termination state itself. So we have got a bunch of states, and we want to learn a termination state that we can actually feed to a planner. And for that, we need to learn a classifier that we can actually hand to a planner, and then the planner can just crank and plan to the termination state that's learned by the classifier. So this is what the 2D clusters might look like. So this is the 2D representation of the clusters represented by PCA. We can see that different points in the clusters refer to different types of terminations where there's an object in front of the robot. And the different states represent the different points in time when there was an object in front of the robot and the robot could not navigate further. And these would represent some sort of an open corridor where the robot can keep walking unfettered until a future, at least until for like a long amount of time. So what's really cool is once you actually get these clusters and learn a classifier, you can actually visualize the states that you get out of them. So this is what the states that create the end of corridor classifier look like. And this is what the states that create an open corridor look like. But what we had was we had two symbols for turning left. And this was because we collected only 75 trajectories, and some of the trajectories had an office door right over here that was closed. And so sometimes when it turned left, there was an office right next to the robot, and sometimes there was nothing in the corridor. And because we're learning this based on the actions that the robot took, we ended up learning two different left symbols instead of just one left symbol. And we'll talk about how we can try to solve that problem next. But this is what happened. We learned two left symbols, one end of corridor and one open corridor symbol. And then we use translation to go from language to the sequence of symbols. So we translate natural language to the sequence of symbols using traditional seek-to-seek methods. And we used glove vector embeddings because we did not really have that many language commands to begin with. So we use glove vector embeddings to get some sort of a boost when mapping language to these symbols. So given that we have the sequence of symbols, we can just execute the symbols in order. And the way we execute them is that we just hand them to a point-to-point RRT planner that gets planned at the low level. For turning right and left, we actually use dynamical movement primitives just to show that you don't always need to plan at the low level. Even though you have termination classifiers, you don't actually need to always plan. You can actually use the demonstrations to learn policies, and then it could be a mixture at the low level to use policies or planning, whatever suits you. So here are some statistics. We had about 913 language commands. 347 of them were novel words. We only had about 75 trajectories. And the exact symbol match accuracy that we got was only 75%. And majority of the errors here were because there were 2 left symbols. And when you're translating, you don't really know which left symbol to map to. And this is after 5-fold validation. So we don't exactly know which left symbol to map to, and that's why our translation accuracy is that low. The way we actually want to fix this error is provide a context of the world when you're doing the translation problem, which would basically be the map of the world. And the other way that people can solve this is with data, where you collect a lot of data and then you finally learn that after you take left, actually sometimes there's a door and sometimes there's not a door, and you represent both of them in the same symbol. And the unsupervised pipeline can actually do that. Then we tested this approach on a novel environment, which was at least 10 centimeters wider than previous environments. And this is important because all the data is lidar data. So this is what the demo looks like. So we give a command that says drive straight until you get to the wall, and then take a left and go down the hallway, take a left, and then stop at the water cooler. And so our symbols are not meaningful. They're just some high-level symbols, like 0 represents going straight and 2000 represents taking a left. They don't mean anything. They're just associated with the termination classifier. And as soon as the RRT planner hits the termination condition, it just stops functioning for that skill, and then we pick the next skill to plan over. And that allows this to be really, it doesn't matter how many actions the agent needs to get to the goal. So this trajectory is thousands of time steps when actually mapped out. Those are some really long corridors, and it doesn't matter what the length of the corridor is. The agent can dynamically plan in any environment. And it never saw this corridor before it planned over here. So then to show that we can actually do this on a larger state space, so over there we only had 90 continuous variables for the lidar data. We also tried this out on a lidar data set, which was 360 dimensional because it's 360 degrees. We were able to learn termination conditions over here. We were able to learn 3 crisp termination conditions of reaching an intersection, taking a right, and taking a left. The only problem was that we couldn't plan over this because we did not have access to a simulator for this domain or the set of actions that the agent actually took. So we couldn't really plan on this domain, but we would like to do something that's in a higher dimensional space than just the 90-degree lidar data that we have. So that's what we want to do. We want the robot to learn how to understand novel concepts and learn novel skills on novel objects. And we think that our pipeline is along the way of getting there, but clearly it needs more improvements. Some future work that I'm actually looking at right now in this direction is the first question that I was interested in is, how do people teach abstractions to a robot? Like, how do people teach these symbols to the robot? And this is because I created the demonstrations previously, and I wanted to see how do people give demonstrations, and can people do these demonstrations with abstractions so I don't have to go through a giant pipeline to learn underlying skills and things like that. And we have found that people are terrible. Generally, they're not giving abstractions to begin with. And when you beg and cajole them into giving abstractions, the kind of abstractions they're giving are not really useful for robot learning. There is a correspondence problem in teaching abstraction, and we're trying to see if that correspondence problem can be resolved somehow. The second work that we're looking at is compositional task learning with language. And this is more of a classic end-to-end deep learning type of a pipeline where we're trying to learn some Boolean compositional functions that are actually part of prior work. And then we try to solve novel commands given these Boolean compositional value functions and solve novel commands in the reinforcement learning scenario. And this will be at the AAAI Fall Symposium workshop in, I think, a month. So again, I have a long list of collaborators across Brown, Georgia Tech, WITS in South Africa, and Vanya, who's at UT Austin now. So thanks to all of them. And so this is the conclusion slide, basically. So we have attempted to learn a generalizable symbolic concept using that are useful for navigation and planning from unstructured demonstrations. Then we map language to sequences of these symbolic concepts. We then plan the sequence of symbolic concepts using some external planner. And our approach allows all this learning to happen without explicitly specifying how many skills or symbols you have, with very little data and no simulator, basically. Thank you.